You hear me?
Yes.
Yes.
Okay, let's start with whiteboard. Yes. Today okay, thank you for homework. I receive all homework. Yeah, and I put some comments during the next week to Moodle. Yes, and let's solve the third exercise from homework. I only show you what you need to do on exam, or for example on the test, if you don't have MATLAB. Yeah, and you need to prove if this system is stable or unstable. Sorry. Okay, for example, this. Let's x1 dot equal to minus x1 and minus x1 and minus x1 cubed plus x2 and x2 dot equal to minus 2 x1 minus x2, yeah, and then we calculate the Jacobian, the x equal to minus 1 minus 1 plus 1 minus 2 and minus 1, yes, and then in 0 0, yeah, always here it's 0 0, yeah. And then minus 1 minus lambda minus 1 minus lambda minus minus 2 1, yeah, and equal to, and we know that it's lambda 2 lambda squared, I think minus, I think plus 2 lambda, yeah, and plus 1 and plus 3, yeah, I think something like this, yeah. And on this step you say okay here, okay, someone have a problem with whiteboard, and now all of you have a problem with whiteboard or something? Someone sees this information, this equation on whiteboard?
Me too.
Okay. Okay, I make, you know, maybe I can share only this my one moment. I stop it and maybe screen, and maybe now it's okay.
I mean, it's okay, but the whiteboard was probably better because anyone can zoom in, zoom out, and move anywhere they want.
Okay. And what I need to do, because when I put on whiteboard this equation, yeah, someone, maybe 15 of you see my whiteboard, I think, yeah. But some part of students do not see, yeah. And I don't know what is the better when I share this whiteboard, yeah, or share this whiteboard. Okay, I try one more. It's good, yeah. Okay. Now you see this, yeah. Okay, let's. Okay, and here you only one moment. And here you always say, okay, this polynomial is stable because all coefficient is positive, yeah, and you don't need to do anything, yeah. Only say, okay, it's stable, yeah, because sometimes you don't have MATLAB and can evaluate this eigenvalues fast, yeah, and it's okay if you only say that this polynomial is stable, yeah. Okay, let's. Do you have any question here? Okay. Okay, I can move this. Okay, and okay, the second one, x1 dot is equal to x2, and x2 dot equal to minus x1 plus x2, 1 minus 3x1 squared minus 2x2 squared. Yeah. And now we need to check all equilibrium and use the indirect Lyapunov method to check the stability of the system. And let's find the equilibrium. Okay, we can see that it's only one. It is only one equilibrium. X1 dot equal to x2. If x1 dot 0, then x2 equal to 0, yeah, and here x2 equal to 0, and then only this minus x1 equal to 0, yeah, and only one equilibrium point, x2 equal to 0 and x1 equal to 0. Yeah, and now the equilibrium of origin 0, 1, this dx, yeah, equal to 0, 1, this is minus 1, and here it's only 1. And again we use the same, minus lambda, 1 minus lambda, minus 1 equal to minus equal to lambda squared, lambda squared minus lambda squared minus lambda plus 1 equal to 0, yeah? And we can see that this system is unstable because this polynomial is unstable, yeah? Because the coefficient near here 1, minus 1 and 1, here is minus 1, and we see that it's unstable, and the eigenvalues lambda 1, lambda 2 equal to 1 divided 2 plus minus g, yeah? Okay. Any question? Okay, the next sorry. Okay, the next equation, the next system is x1. Okay. x1 dot equal to 2x1 minus x1 x2 and x2 dot equal to 2x1 cubed minus x2. Okay. Okay. And you only rewrite this equation in the form is equal to x1 2 minus x2, yeah, and this one is stay, okay, and x1 dot equal to 1 equal to 0, yeah, and here x1 it's only when x1 equal to 0, yeah, or when x2 equal to 2. Yeah, and when we solve this equation, we can find this 3 equilibrium point. The first one is because x1 0, x1 0, x2 0. Yeah, first one x1 equilibrium point equal to 0 0, the origin. Okay, 0 0. x2 equilibrium point equal to, okay, if here is 2 and 2 here 2, and it's equal to 1 and 2, and the third one is equal to here is 2 and x2 is state 2, but here it's 1 or minus 1, yeah, minus 1. Yeah. Any question here? Okay. And let's analyze this all. The stability in the local stability of all these equilibrium points, and dx Jacobian equal to, here it's 2, and here it's minus x1, yeah, and here it's 4 x1, yeah, and minus 1. Okay. Okay. And now Jacobian in 0 0 equal to 2, 0, 0, and minus 1. Yeah, and lambda 2 minus lambda minus 1 minus lambda equal to 0. And we can see that the eigenvalues is 2 and minus 1. Yeah, lambda 1 equal to 2 and lambda 2 equal to minus 1. Yeah, this equilibrium point is unstable. It's a saddle point. Okay, and the next one, let's analyze the next equilibrium point, dx, and in 1, 2, it's equal to minus yes 2, and okay 2 and minus 1 and 4 and minus 1. I think it's correct. Yeah. And
sorry. Hello?
Sorry. 2 minus 1, 4 and minus 1. Any question?
Sorry? Hello?
Do you have some question?
Yeah, I think you made a mistake in the first derivative in Jacobian.
Here?
In the it should be like 2 minus x2, the first.
Here, 2 minus. Here is 2 minus x1, 4x1 and minus 1. I think it's correct. Or
When you do a derivative of the first one, where is 2, shouldn't be like 2 minus x2.
Yeah, you're right. Yeah, I'm sorry. Yeah, exactly. Here it's 2 minus x2. Yeah, thank you. Yeah, 2 minus x2 and here it's okay, but here it is 2 minus x2, 2, and what does it mean? Yeah, here is 0. Yeah, you're right. Okay, it's 0. Yeah, I think now it's correct. Oh, sorry, only check. Minus 2 minus x2 minus x1. Okay, now it's okay. Okay, and it's equal. Okay, and eigenvalues, it's minus lambda, minus 1, sorry, minus 1 minus lambda, and minus 4 minus 1, and equal to 0, and lambda squared plus lambda and plus 4, yeah, equal to 0, and we know that all coefficient is positive and this equilibrium point is stable. Yeah. Okay. And the next one is okay. X, it's -1, 2, equal to 0, because 2 minus 2 equal to 0, and 1, and only here -4, because 4, because here is for x1, yeah, and for x1 minus x4, yeah, minus x4, and here it's -1, yeah. And let's find the eigenvalues. Minus lambda, -1 minus lambda, and -4. Okay, -4, -4, 1. Okay, -4, 1, and it's equal to lambda squared plus lambda and plus 4, yeah, equal to 0, and it's the same like here, yeah, and this equilibrium point is stable, yeah. And if we calculate in MATLAB, we can find that the eigenvalues lambda 1, 2 equal to minus 0.5 plus minus 1.24 and G, and this equilibrium point is stable focus, yeah, because not only real part, but only and imaginary part too, yeah, here. Any question? Okay. Okay, the next system. Okay, consider the system x1 dot equal to minus x1 minus x1 squared plus 1 minus x1 minus x2. Okay, and x2 dot equal to minus x2 minus x2 squared plus 1 minus x1 x2, sorry, minus x1 minus x2. Okay, and fun, let's find all equilibrium points in this example. Okay, if we use a MATLAB, yeah, we can put not MATLAB, but here we need to solve. Okay, I think you can do it at home. This system, yeah, it's a last system when we check the stability, the local stability by the first Lyapunov method, yeah, and you can try to find all equilibrium point of this system and determine the tip of each point, and you can construct the phase portrait and can to determine the qualitative behavior of system, yeah, and you can do it at home. And now we start with the second Lyapunov method, I think, yeah, and let's solve some systems with second Lyapunov method. Okay. Okay, here I use the example from our first seminar. Yeah, you can find this all example in PDF on Moodle. Yeah, and on first seminar we only check the stability of equilibrium points by the first Lyapunov method. By now we try to check the global stability of this system based on the second Lyapunov method. Yeah, and let's try to this first equation from first system from the homework. From first seminar, x1 dot equal to 2x 2 cubed minus x1 in 5 degree, and x2 dot equal to minus x1 minus x2 in 5 degree. Yeah, and when we use another Lyapunov method, we can find that the final step is lambda squared equal to 0, yeah, and lambda 1, lambda 2 equal to 0, yeah, and we can't say anything about the stability of the system under the first Lyapunov method, and then we can use the second Lyapunov method. Let's take a positive definite function v from x equal to x1 squared plus x2 in 4 degree, and then calculate the derivation from x equal to 2x1 x1 dot and plus 4x2 cubed x2 dot, yeah, and it's equal. And now put this first and second here, yeah, and 2 and the first one 2x2 cubed minus x1 in 5 degree and plus 4x2 cubed, and here x1, yeah, x1 4x2 cubed minus x1 product minus x1 minus x2 in 5 degree. Yeah. Any question here on this step? Okay. And it's equal to 4 equal to 4x1 x2 cubed minus 2x1 6 degree, yeah, and then 2x1 4 2x1 and minus okay, and minus 4 x1 x2 cubed and minus 4 x2 in 8 degree, yeah, and it's equal to, okay, here this 4x1 x2 cubed minus this one, and stay only minus 2x1 in 6 degree minus 4 x2 8 degree, yeah, and this is less than 0, yeah, for all x1 x2 not equal to 0, and therefore the system is globally asymptotically stable, yeah. Any question? Okay. Let's take another. I only write this. Only write this system. Sorry.
Excuse me, can I have a question?
Yes.
Now you told that the system is asymptotically globally stable, but
Yes.
with the first method, the indirect method, you told when the real part of the eigenvalues were negative, you told just that the system is exponential stable. Why?
Okay, I understand. Yeah, good question. When we use the first Lyapunov method and the real part of the eigenvalues is negative, we can conclude that this system is local exponential stable. Yes, it's correct. But with this method, we can prove the global stability of the system, but only asymptotical stability. Yeah. Why? Because we can prove the global exponential stability of this system, but we need to use some extension. Yeah, we need to find some constant C1, C2, C3. But now on lecture, I think you only in this phase that you only know how you can prove the global, if how you can check if the system is global asymptotical stable, but we can do it on the next week on seminar. I show you how we can prove the global exponential stability of the system. Okay, but now we only prove the global asymptotical stability of the system, and we can do it with this Lyapunov function. Yeah, with this second Lyapunov method.
Okay, thank you.
Okay. Okay, and now I can show you a fast example, a linear example. Yeah, it's x1 dot equal to x2 and x2 dot equal to minus x1. Yeah. And I know that you know that this system is stable, yes? Can you calculate the eigenvalues of this? Of eigenvalues of Jacobian? Okay, if dx, we know that this is the pendulum, yeah, the oscillator, linear oscillator, yeah, and equal to linear system, and 0, 1, minus 1, 0, yeah, and we know that only x2, sorry, maybe only x2. Yeah, this is a linear oscillator, yeah. And 0, 1, minus 1, 0, and let's find the eigenvalues, and we know that lambda 1, 2 equal to plus minus g, yeah. And this is the and when we check with first Lyapunov method, we can say, okay, this system is stable, yeah, Lyapunov stable, and we know that if this system is linear, then the stability is global, yeah, for this kind of system. Yeah, but we can try to apply the second Lyapunov method. I only want to show you how we can apply. Okay, and okay, v from x equal to x1 squared plus x2 squared, 2 divide 2, and v from x, v dot from x equal to x1 dot plus x2 dot, yeah, something like this, and it's equal to x1 and this and x2, yeah, and plus x2 and minus x1, yeah, it's equal to 0, yeah. And it is only simple example, yeah, and you can see that this v dot equal to 0, and what we can say about the system. Anyone know? Maybe I want to ask someone. Okay. It's 0 or yes, but it's for all. Okay, it's for all x1, x2, yeah, not equal to 0. But when we found that this v dot x equal to 0, we prove the stability of the system, yeah, with the second Lyapunov method, because here, okay, we can prove the stability. This system is Lyapunov stable or simple stable in sense of Khalil, yeah, in Khalil book. And for example, when we check it in some nonlinear system and found that v dot x equal to 0, then we can say that this system is global stable, yeah. I only show you on some primitive example, yeah, linear, how we can use this second Lyapunov method for proving the stability, not asymptotical stability of the system, global asymptotical stability, but global stability. Yeah, this system is only global stable, but we can show it with first Lyapunov method because this system is linear, and this first Lyapunov method we found that plus minus E or G, and we know that if this is linear, then it's the behavior is global. Yeah, this behavior. Any question? Okay. Okay, the next example, the second one from the first seminar, x1 dot equal to x2 and x2 dot equal to minus x2 cubed minus x1. Yeah, and okay, when we calculate, when we apply the first Lyapunov method, we found that lambda 1, 2 equal to plus minus E or G, and we can say anything about the stability of this system. And let's apply the second Lyapunov method. Vx equal to, let's take Vx equal to x1 squared plus x2 squared. Yeah, and then calculate v dot equal to 2x1 x1 dot plus 2x2 x2 dot, and let's put this x1 dot and x2 dot here, and 2x1 x2 and plus 2x2, and this one minus x2 cubed minus x1. Yeah. And it's equal to, okay, 2x1 x2 plus 2, sorry, this minus minus 2x1 and minus 2x2 in 4 degree. Yeah, and you can see that it's equal only to minus 2x2. Okay. Okay, and now we can say that it's less than 0. Yeah. Sorry. Okay. Only this. Okay. It's less than 0. For all x2 not equal to 0. Yeah. And what we can say about this system? It's stable or unstable?
Asymptotically stable.
No.
No?
No. We can say, but we can say that it's stable. Yeah, only stable, because here not this x1. Yeah. Because when it's minus 2x2 in 4 degree, for example, minus x1 in squared, then we can say, okay, it's global asymptotical stable, but now not. Yeah, we need to apply the LaSalle principle. Today, Professor Cherkovsky said something about the Lassala principle on lecture, but I can show you how we can apply this Lassala principle here. This is principle of invariant, and okay, we can say x2 go to 0. Yeah, we know that x2 go to 0 here, and if x2 okay, x2 in time is equal to 0, and then x2 dot from time go to 0, 2, yeah, equal to 0, 2, and then, but we know it from this. If x2 go to 0, then x2 go to 0, and here x2 go to 0, and this x2 go to 0, and this x1 go to 0 too. Yeah, because here it's 0, 0, and you know, if this 0 and this 0, then this is 0 too. Yeah, and we can say that x2, we can say that x dot time equal to minus x2 cubed t minus x1 t, yeah, and from this is go to 0, 0, this 0, and from this x1 from t go is equal to 0 too. Yeah, and then we prove the global asymptotical stability of the system. Yeah, and now we can say, okay, this system, when we apply the second Lyapunov method, we found that v dot x equal to minus 2x2 in 4 degree. It sets for then 0 for all x2 not equal to 0, and from this we conclude that x2 from the equal to 0, and x, if this equal to 0, then x2 dot equal to 0, equivalent to 0, and then we can see from the second equation from this system that then x2 dot equal to minus x2 cubed minus x1, and if x2 equal to 0, this part equal to 0, then this equal to 0 too. Yeah, any question? Okay, let's calculate the another example. Let's solve the third one, x1 dot equal to x2 minus x1 cubed, and this x2 dot equal to minus x1 oh, sorry. Global asymptotical stability. Yes. Yes, yes, yes. In this step, we can say that this system is global stable. Yeah. Uh-huh. Okay, okay, sorry. I don't know. Okay, you don't see my cursor, yeah? Okay, 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 okay. Okay, here. So some trouble with my pen. Okay. Sorry. I need to switch maybe off something. No. Okay. Okay, here only this part, yeah, we need, if this part is minus 2x2 x2 4 minus some x1 cubed, for example, then we can say, okay, this system is global asymptotical stable, yeah, gas. But in this case is only global stable, yeah, without, it's global Lyapunov stable. Yes. Yes, this part is a Lassal principle, yeah. When we say, okay, x2, we know that from this part that x2, this derivative minus 2x2, that x2 go to 0 is x2 equal to 0, and then we say, okay, x2, when x2 equal to 0, then x2 dot equal to 0, and from this second equation, x2 dot equal to minus x2 cubed minus x1 equal to 0. Sorry, not equal to 0, but x2 dot equal to 0 from this part, yeah. This part x2 equal to 0, and then we know that x1 equal to 0 too, yeah. Because 0, 0, and minus something, minus 0, yeah. And then we can conclude that x1 equal to 0, 2, and this is this Lassala principle. Yeah. The second question, you think here? Yes, yes. 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 When we found that x1 equal to 0, then okay, it's asymptotical stable because x1 go to 0. Okay, and the next, you can ask Professor Chilikovsky. Professor Chilikovsky on the next lesson, I think he will show this Lassala principle, yeah. And I only show you now because I can say, okay, we don't know, you know, only that this system is global stable, but it's better than I show you that we can apply the Lassala principle in this way, yeah. Okay, and the second, x2 minus x1 cubed, and this minus x1 cubed minus x2 cubed, and okay, here it's x1, x2 equal to 0, yeah, and we can say anything from the first Lyapunov method, and let's apply the second Lyapunov method and prove the stability. Let's take v x equal to x, sorry, equal to x1 in 4 degree 4 plus x2 in 4 degree 4, yeah, is greater than 0 for all x1, x2 not equal to 0, yeah, and the derivation is equal to, this is okay, x1 cubed x1 dot plus x2 cubed x2 dot, yeah, and it's equal to x1 cubed, x2 minus x1 cubed, and plus x2 cubed minus x1 cubed minus x2 cubed. Yeah, and it's equal to here x minus x1 6 degree minus x2 in 6 degree and minus x1 cubed x2, and here it's plus x always plus x to 3 minus x1 cubed and minus x2 6, yeah, and okay, and what's here? Okay, let's try another. It's not so good with this Laplace function. Let's try another Laplace function. V from x equal to x1 in 4 and plus x2 squared x2. Oh, sorry, 2. Only 2. And this is Vx and Vx dot equal to 4x1 x1 dot plus x2 dot, and is equal to x1 cubed, and then this is x2 minus x1. Okay, this x2 minus x1 cubed and plus x2 minus x1 and minus x2 cubed. It's equal to x1 cubed x2 minus x1 6 and plus not plus but minus x2 x1 cubed and minus x2 4, and it's equal to what we can see, that we can this term and this term and only minus x1 6 minus x2 4, and therefore it's for all x1 x2 less than 0, yeah, for all x1 x2 not equal to 0, yeah, and this system is global asymptotical stable. Yeah. Any question? First, I try another Lyapunov function, and I found this. But I think we can prove that this is a negative definite. But I have more time, and I show you how we can check if the function is the polynomial is stable or unstable. Yeah, is positive definite or negative definite. We can check it in future, but now only this kind of calculation. Yeah. And any question? Okay, let's do another. This x1 dot equal to minus x1 minus x1 cubed. Yes, and we know that we can prove the local exponential stable, but by the first Lyapunov method. Yes, and we can apply the second Lyapunov method and prove the stability of the system, global stability of the system. Yeah? And v from x equal to 1/2 x1 cubed. Yeah, and v dot from x equal to x1 dot is equal to x1 minus x1 minus x1 cubed equal to minus x1 minus x1 in second degree minus minus x1 minus x1 4. Yeah, and we can conclude that this system is global asymptotical stable because this is less than 0. Yeah, for all x1 x2 not equal to 0, only x1, sorry, in this way. Okay, we can try to prove the stability of, maybe at home you can try another system, or we can start here and, for example, x1 equal to minus x1 plus x1 cubed. Yeah, and we can find that v dot from x, the same Lyapunov function, equal to this minus x1 cubed, squared plus x1 cubed. Okay, and it's equal to minus x1 squared 1 plus, minus equal to 1 minus x1 cubed. Yeah. And we can see that this function is negative definite only if x1 greater than -1 and 1. Yeah. On this interval, this function is negative. On this interval, this function is negative definite. Yeah. This function v dot negative definite if x1 is greater than -1 and 1. Yeah. And on this interval, this function or this system is local asymptotical stable, but we know this interval. Yeah. When this function is stable. Any question? Okay. Okay, next example. X1 dot equal to x2 minus x2 squared. X2 dot equal to minus x1 plus x1 x2. Okay, when we if we use when we used the first Lyapunov method on first seminar, we found that in this system x lambda 1 2 equal to plus minus g. Yeah? And we can say anything about the stability of this system with first Lyapunov method, and now we apply the second Lyapunov method. Let's take function v x equal to x1 cubed plus x2 cubed, and we. Some question?
Yes, can we go through some examples of the variable gradient method to calculate the Lyapunov function?
Okay. I can prepare the example to the next seminar. Okay.
Okay, thank you.
Okay. Now we calculate only some simple systems. Yeah. Okay. V dot from x equal to 2x1 dot plus 2x2 dot. It's equal to 2x1 here minus x2 minus x2 squared and plus 2x2 and x2 dot minus x1 plus x1 x2. Okay, and it's equal to 2x1 x2 minus 2x1 x2 squared plus 2x1 x2 squared minus 2x2 x1. Okay. Okay, and this one and go up, and it's equal to 0. What we can say about the stability of this system? It's a question. Can someone try to say?
Well, it's stable because it's 0 everywhere.
Okay, it's stable, it's global stable, yeah? Global stable, yeah? It's global Lyapunov stable or global stable because the derivation of V equal to 0. It's something like when we check the example with linear oscillator, yeah? This system is global stable. Global stable or global Lyapunov stable, you can say. Yeah, it's the same. Okay, thank you. And maybe we can stop for this kind of examples. Yeah, and I can show you. Yes.
Now, from the V derivative, we see that the system is Lyapunov stable, as you said. But is it possible to find some other polynomial which will get a negative definite function?
No, because here, yeah, in this example, it's a very good example, yeah, and here we found some polynomial, this polynomial, and when we calculate the derivative, we found that it's equal to 0, and we know it's stable. Another problem when you take some polynomial and can't say anything about the system on the last step when you calculate this derivative, yeah. But in this example, it's okay because you found that x equal to 0 and you don't need to solve anything. Yeah, this system is global stable. Yeah.
Okay.
Okay, thank you. And I want to show you, because today on lecture, Professor Tchaikovsky says something about the positive definite function, yeah, negative definite function, and I show you how we can check if the function is positive definite or negative definite. Yes. Let's maybe some Sylvester criterion. Sylvester, yeah, you know this Sylvester criterion in Czech. Yeah, and we can apply this criterion when we take some quadratic form as Lyapunov function. Yeah, and now I only repeat some information about this, that okay, some form Vx equal to x transpose and q matrix qx, and this quadratic form is positive definite if and only if all determinant 1 equal to q11. Sorry, you can check on, for example, on the internet, in Wikipedia or something like this, Sylvester law criterion. Yeah, this C V T X criterion. Yeah, the Sylvester's criterion. Check it. Yeah, and I only want to repeat this is greater than 0, and let's the second equal to some q11 and q12, q21, q22, yeah, and so on. This 3 point something, and determinant q, yes, better than 0. Yeah. In this case, this quadratic form is positive positive definite. Yeah, and let's check some quadratic form. Yeah, any question here? In this step, you can check the Sylvester's criterion